Welcome to the final session of the live sessions for the course Introduction to Information Theory on the NPTEL platform. I'm your TS Sachin from the Indian Institute of Science. And in today's session, we'll just summarize all the things that we learned in the lectures throughout the course and write down all the important results so that you can use it as material for revision before your exams. There won't be any problem solving or new materials in this session. It's mostly just a summary lecture. The first lecture was the introduction lecture. These are the reference books that we have used for this course. Applied Digital Information Theory, James Massey, which is available online, and Elements of Information Theory, a pretty standard textbook for information theory courses. Other references are Gallagher, Young, and McKay, but most of the things are from James L. Massey's notes and Thomas and Thomas and Cowell textbook. So the topics that have been covered are introduction, where we introduce entropy, relative entropy, mutual information, a few information inequalities, coding, source coding, so block to variable length coding, with Huffman coding as the example of optimal coding, variable to block length coding with Anstal coding as the optimal coding, variable to variable length coding, which you have seen Lempel-Ziv codes and arithmetic codes, block to block length coding using typical sequences, for which you use the asymptotic equipartition property. Then we saw coding for sources with memory. So up to that is source coding, which is one of the major problems that we deal with in information theory. The second major problem that we deal with in information theory is the capacity of a channel, and this is more on the communication side. You could say the coding is more on the channel part of the coding. So in a communication system, you have a source and then a source encoder, then a channel encoder, after which you have a channel, followed by a channel decoder and source decoder. So the first part has to do with source encoding and source decoding. The second part has to do with the channel encoding and channel decoding. We don't really see techniques of encoding for channel encoding. We only see the capacity of a channel and a proof for the capacity, which mostly has to do with the random coding proposed by Shannon. Actual coding theory techniques will be left to the course on error control coding or coding theory, which is also offered on NPTEL, which should be offered next semester. So one semester offers information theory course, and the next semester continues that with the coding theory course. So from this course, we saw our expectations were to find the fundamental limits of communication, fundamental limits of data compression, practical source compression algorithms, and some mathematical techniques that you need if you are going to work in this field. And I hope we have met these expectations. We gave uh, limits of data compression when you're doing block to variable length to block, variable length to variable length, and block to block coding. We gave upper and lower bounds. Sometimes we also gave conditions for which you can achieve upper and lower bounds and some coding techniques which give you optimal data compression. We also saw channel capacity, which is the fundamental limit of communication. So we saw that the limit of data compression, the bounds on data compression were functions of the entropy of the source. So the answer to that question depends on entropy. And if you ask what is the fundamental limit of communication through a channel, then the answer to that comes from the channel capacity. So these are the two quantities that we are most interested in information theory. And as far as mathematical techniques are concerned, we saw a lot of results we can use to prove inequalities and also saw quite a number of proofs, which were, in a sense, were rigorous enough, I guess, for anyone doing engineering in information theory or research work in information theory. First lecture was the introduction and basic blocks of communication. There are three steps in any form of communication: encoding a message at its source, transmitting the message through a channel, and decoding the message at its destination. Information theory will answer two fundamental questions: what is the ultimate data compression, and what is the ultimate transmission rate? First, we have to quantify what information is. That is also something that information theory does. So, if you flip a coin that has only heads, or if you flip a coin with bias one, where you always the result is always heads, does flipping the coin convey any information to you? It doesn't really do that because you already know that every flip of the coin is going to be heads. So once someone flips a coin, you don't need them to reveal the coin to know that it's going to be a heads. Similarly, if a source produces successive bits of pi, then there is some algorithm to calculate the successive bits of pi. As long as you know what algorithm that is, you can get the same digits without it being communicated to you. So as long as you have a deterministic process, then there is no deterministic experiment, then there is no information being conveyed from the experiment. So information can be conveyed by a source only if there is some uncertainty in what the source can transmit. For example, if uh, one of your friends is sending you a movie and you know that he only has one movie in his laptop, then you already know what movie that is going to be sent. So you could always search for it somewhere else. So when he sends you the movie, you don't really get any information per se. But if he has a database of movies, different movies, and he sends you only one movie, then by observing the content that is being sent, you can know which movie is actually being sent. Because different movies have different content, I mean, that's not a very clear example. Suppose uh, you have 10 different files, and each of those files differs only in uh, a, a packet of data in the middle of the file. Or maybe there are 10 different videos, and each of those videos is exactly the same for most of it, but it's only different in the last minute. So only by observing the last minute of the video can you make out which of the videos was actually sent. So by looking at the last minute of the video, you know whether he sent the first version of the file or the second version of the file. You can make out a difference. So you get some information from that. But if all the videos were identical, then by observing the videos, you wouldn't really know which of the videos he sent you. If you had 10 copies of video of the same video, then by looking at the video, you wouldn't know which of the copies were actually sent. But if there were some differences, slight differences between each of the copies, then by observing the entire video, you could tell which of the copies was sent. So there was a mapping between the copies and the uh, file indexes. Say, then you could say what the file index is by looking at the actual content of the video. So anyway, only when there is uncertainty in the source can you make out any information. Otherwise, the source gives no information. That's why throughout the entire course, we assume that the thing we are sending is a random variable that can take multiple values with each value having a certain probability associated with it. Here is the information source. From the source, you do encoding and you get code words from that. If you're doing cryptography, there might be some encryption that will again give you a code word. From that, you do channel encoding to correct errors. After that, you do digital modulation. And then in the receiver side, you do all these processes, the opposite inverse of these processes in the reverse order. Why we need source coding? What is the function of source coding? It is to minimize the number of bits per unit time required to represent the source output. The source information might be in various formats. Uh, it might take various different values. It might not be suitable to represent or store or transmit. The source coding will change the information into a format that is suitable for coding, such that you use suitable for transmission or storage, and usually you will transmit or store in terms of bits, and the aim is to minimize the number of bits required to represent the source output. Encryption is to secure the transmissions you are sending against eavesdroppers access, who might also have access to the transmissions. We have to make sure that only the receiver is able to decode the useful information from the uh, transmitted signal, and anyone in between is not able to do that. That is done usually through RSA systems a lot of the time, where there are keys that only the sender and receiver will have, and you can only decode the right information when you have the right key. But guessing the key is much harder. So, and it's a very low probability event. So, if someone in the middle can't really guess the key within any useful amount of time, and so they won't be able to decode the information that you are transmitting or intercept the information you're transmitting. Function of channel coding is to make sure that errors introduced by the channel can be combated, which you do by adding extra bits to the information sequence, and by using these extra bits, using them, you can manipulate them, you can add them correctly, you can add them in a clever way so that uh, if the number of errors is within a certain range, then you can always correct those errors. So when you're designing channel encoder and decoder, so first you look at the type of information that is being transmitted and the channel, etc. And then you figure out what are the errors that can occur, how many errors can occur with high probability. So for your requirement, for example, for audio transmission, human beings can make out uh, the correct human beings can make out whatever is being transmitted to them, even if there are slight errors or distortions in the received signal. So now, right now, I am talking to you, and it's just being transmitted through a channel and then being stored at the server. Then maybe you're accessing it through uh, your data on your mobile. There might be errors introduced by the channel there. So error control coding ensures that uh, if there will be some probability of errors occurring, and usually a large number of errors occur with lower probability. So there is some kind of threshold where if the probability of occurrence of say t errors less is greater than or equal to some probability p, which is allowable. So that amount of distortion is still fine for the user, for the receiver, and you will only be required to correct t or lesser number of errors. More than t errors might occur with a smaller probability, and that might not affect your application. So once you have this parameter t, you just need to ensure that all t errors are corrected. That is done by a channel encoding and channel, channel encoder and decoder. Then there's the modulation part where you have to transmit through antennas, or even if you're transmitting through broadband or optical fiber, you can't just, most of the times, you don't just transmit. Uh, there's the method you transmit bits is through electrical signals and mapping between the bits to the electrical signals or set of bits to electrical signals involves some kind of modulation or different kinds of modulation, PSK, which if it's binary, it's BPSK, QAM, QPSK, quadrature, phase shifting, etc. This comes under the digital communication, which hasn't been covered in the course, and we also don't go over any cryptography techniques in this course. So the in this course we use mostly Shannon's measure of information, where you have a random variable x and it takes values from some alphabet script x with say L, capital L values. Then if pi is the probability of occurrence of the ith value of x, then the amount of information provided by x is summation pi log pi mi equal to 1 to l, negative of this. And this particular function is called the entropy of the random variable x. Now, since pi can also be 0, we log 0 is not defined, therefore we only sum over non-zero values of probability. So for that, we define the support of f to be the subset of its domain where it takes non-zero values. So the support of p of x, which is the probability density function, we only consider those values and some overall values in the support, p of x log p of x, which is nothing but the expected value of minus log px of x. So the entropy or uncertainty in a discrete random variable x is h of x equals minus summation of px of x log px of x, where small x belongs to the support of px, which can also be written with the notation expected value minus log px of capital X. That's this notation. That is only for one variable. If you have two random variables, we define a quantity called the joint entropy, which is defined as h of x comma y, is denoted by h of x comma y and defined as the expected value of minus log pxy of x comma y, which is, when you write that out, for all xy in the support of the joint distribution pxy of x comma y log pxy of x comma y. And we have if script x is 0, 1, or if script x is doesn't have to be 0, 1, it can be any two values. Let me just write 0, 1 as the standard. And px of x equals 0 is 1 minus px of x equals 1 is px is, sorry, x of 0 is 1 minus px of 1 is p. Then the binary entropy function is defined as h of p is equal to is denoted by h of t and defined as minus log. It's h of x for this particular type of random variable which takes two values, one with probability p and the other with probability 1 minus p. So it depends only on p. Therefore, we write h of p. It is actually h of x. H of p is only notation for the binary entropy function. Its value is minus p log p minus 1 minus p log 1 minus p. So all the while we are using log to base 2, and if you use log to base 2, these are called bits, the units of bits. If you use other bases, you get other units. So the base also matters in all these expressions. Then we have the IT inequality. It says for a positive real number r, log of r less than or equal to r minus 1 log e with equality if and only if r equals 1. I won't go through proofs. This is just a summary lecture. You can go to the corresponding lectures and see the proofs. And we have properties of entropy. If the discrete random variable x, so from now on I'll write discrete random variable as drv at L possible values, that is cardinality of script x from which x takes the values of L, then h of x lies between 0 and log L with equality if and only if px of x equals 1 for some. So equality on the left, there are two equalities here. With first I'll write conditions for equality on the left, and that is px of x equals 1 for some x, and equality on the right is f of fx of x, px of x is 1 over L for all x in script x. We can prove that using the IT inequality. Another property is if you take the entropy by taking log with respect to base b, and that is equal to log a base b times the entropy of x to the base a. Next, we define the conditional entropy of the discrete random variable x given the event y equals y, h of x given y equals y is summation of p of x given y log of p of x given y xy belong to x belongs to support of the conditional distribution, which is equal to the expected value of minus log of px given y of capital X given capital Y given y is equal to y. Then we have the conditional entropy of the discrete random variable x given the discrete random variable y, which is the average of conditional entropy of x given the event y is equal to small y, average over all possible values of capital Y, small y. So it is h of x given y is summation over all y in support of py, py of y into h of x given y equals y, which can be written as the expected value of minus log of p of x given y of capital X given capital Y. Then we have the relative entropy if x and x hat are discrete random variables with same set of possible values, then and distributions Px and Px hat, the relative entropy d of Px parallel to Px hat is average value of log of Px by Px hat, average over all x in support of Px. We have a result on the divergence. This is also called divergence relative entropy, and there is an inequality involving the divergence between two distributions. For any two distributions P and Q, D of P parallel Q greater than or equal to 0 for any two probability distributions P and Q on X with equality if and only if P equals Q. That is Px of x is equal to Qx for x for all x in the set of values script x. Then we have the chain rule. Chain rule for entropy is h of x1, x2, etc. xn is summation h of xi given x1, x2 up to xi minus 1, where I ranges from 1 to n. Then we have the quantity mutual information. ixy between two random variables x and y is summation of pxy of x comma y log of pxy of x comma y by px of x, py of y, where px of x is the marginal distribution, py of y, py of y is also the marginal distribution of y, and x, y are in the support of pxy, which can be written as d of psi parallel px py. Right, that you first have to ensure that pxx into py is also a probability distribution, which can also be written alternatively as h of x minus h of x given y over h of y minus h of y given x is equal to I of y x, and it can also be written as h of x plus h of y minus h of x comma y. We have that I of xy is greater than or equal to 0 with equality if and only if x and y are independent. This comes from the fact that I of xy is the divergence between pxy and pxpy. So divergence is always greater than or equal to 0. So mutual information is greater than or equal to 0. Equality holds only if uh, pxy is equal to pxpy, which means x and y are independent. Then you have the chain rule I of x1, x2, xn with y is summation I of xi with y given x1, x2 up to xi minus 1. I goes from 1 to n. And you have chain rule for relative entropy. V of pxy of x comma y parallel qxy of x comma y is equal to d of px of x parallel qx of x plus d of p of y given x of y given x parallel q of y given x y by x, where we first define d of p of y given x y by x parallel q of y is defined as summation pxy of x comma y log of p of y given x of y by x the q of y given x of y by x, not y given x. Or what do you want to call that? Then we look at a few information inequalities. Jensen's inequality. It says if f is a concave function and x is a random variable taking values in some set I, then expected value of f of x is less than or equal to f of expected value of x. Next, we have the log sum inequality, which says for any non-negative numbers a1, a2, etc., and b1, b2, etc., such that sum of ai over all I is finite and sum of bi over all I is finite and non-zero, summation of ai log of ai over bi over all I is less than or equal to summation of ai times log of summation of ai over summation of bi. Using these, we can prove that d of p parallel q is convex in the pair pq. So for lambda greater than or equal to 0, less than or equal to 1, d of lambda p1 plus 1 minus lambda p2 parallel lambda q1 plus 1 minus lambda q2, where p1 q1 and p2 q2 are two pairs of probability mass functions. This is less than or equal to lambda of d of p1 parallel q1 plus 1 minus lambda of d of p2 parallel q2. We also have the result h of p is concave in p. That is because h of p can be written as log L minus d of p parallel u, where u is a uniform distribution. Log L is constant, so minus d of p parallel u is concave because d of p parallel u is convex. Therefore, h of p is concave. Or you can just look at the binary entropy functions graph and you can see that it is concave. Then we have some more inequalities. One is the data processing lemma. It says when XYZ is a Markov chain, then I of XZ is less than or equal to I of XY, and I of XZ is less than or equal to I of YZ. So mutual information between the variables at the ends of the Markov chain is less than or equal to mutual information between any variable at the end and the middle variable. Then we have Fano's lemma. It says let U hat be the estimate of a LRE random variable U, and let U hat also be LRE if P is defined as probability of U hat not equal to U. That is the probability of the set of all outcomes such that U hat of the outcome, any outcome in that set, is not equal to U of that outcome. See, U hat and U are random variables which are functions of the outcome of the experiment. Outcomes can be written as omega 1, omega 2, etc. And the value of the random variable, since x is a function, it's or u is a function, there will be u of omega 1, u of omega 2, etc. For so u hat and u might agree on some outcomes, omega I for some i's, and may be different for different i's. When we say the event u hat not equal to u, it means one of the outcomes in a set of all outcomes where you are and the outcomes not equal to you hat of those outcomes. So this is actually a subset of the sample space. It's a set of outcomes. A probability that a random variable is not equal to another random variable is not, it's a more of an abuse of notation because probability is only defined for subsets of the sample space, or which are events. When you write u hat is not equal to u, you mean the that event of all outcomes for which u hat is not equal to u. Anyway, once you have PE defined, then Fanos lemma says h of PE plus P log of L minus 1 to the base 2 is greater than equal to h of u given u hat. So it's an upper bound on h of u given u hat, you can say, where h of u given u hat is in bits. The equality holds if and only if P of u equals q u given u hat equals u, which is probably that u is equal to uh, let me write u not equal to u, or u is equal to u dash given u hat is equal to u is the same for all values uh, u dash not equal to u. Sorry, it is the same for all values of u. And we could say the equality holds if and only if p of u is equal to u dash given u hat is equal to u, where u dash is not equal to u is the same for all u, and p of u equals u dash given u hat equals u is equal to p of u equals u double dash for u hat equals u for any two distinct values u dash and u double dash such that u is not equal to u dash and u is not equal to u double dash. That is, if probability that an error occurs is same for all values that u hat takes, and for any given value that u hat takes, the probability that u takes some value u dash is same for all values of u dash. You can weaken this result by noting that h of PE is less than or equal to 1. So you can write 1 plus PE log of L minus 1 is greater than or equal to h of u given u hat, which means that PE is greater than or equal to h of u given u hat minus 1 divided by log of L minus So that's all we saw in week one. In week two, we saw block to variable encoding. So you have a message source, which is a single random variable u, and you're encoding a single random variable into code words of let w, where w is a random variable itself. So each of the w letters in the code word x1, x2, xw are also random variables. So z is a random vector and also a random variable. The average code word length E of W is defined as the average value of WI, average overall values of average of all code word lengths. Since W is a random variable, it can take, let's say, it's so since U is a carry random variable, it can take K values. For each of these K values, you have one code word. So is assigned to one code word, which has let's say the value ui. You can take values u1, u2 up to uk. Then ui is assigned to some code word x1, x2 up to xw1. U2 is assigned the code word x1, x2 up to xw2. Or you could say it's a random variable uh, x1, x2 up to xw1. You can call it z1. So corresponding to each UI, there is a zi, which is a uh, DRE sequence of DRE sequence of length W. So the expected code word length is sigma WI PO of UI. So the value WI occurs with the probability of PO of UI because WI is the code word assigned to the as information symbol UI. So we want E of W to be as small as possible. So smallness of the average code word length is a measure of goodness of the code. Then we saw what a uniquely decodable code is. So given any sequence, you can always split it into um, unique code words. There is only one way to split it into code words that's uniquely decodable. If you make it a prefix code, then it is always uniquely decodable and it's also instantaneously decodable. That is, as soon as you receive a code word, you know that the code, know what code word has been received. You don't have to wait for uh, any extra number of bits to know whether a code word has been sent to you or not. As soon as you reach the end of the code word, end of a sequence of bits, if it is a code word, then you know that one particular code word has occurred. So you can keep receiving the bits and At each instant of time, see whether the bits you have received form a code word or not, and as soon as a code word is formed from all the bits that you have received till now, you declare that that particular code word has been received and start counting from the next bit. We saw a test for unique decodability, which was explained in class. Then we saw how a DRHC prefix-free code can be there's a one-to-one correspondence between a prefix-free code and a set of leaves in a DRHC. So examples of a prefix-free code. Then we saw the Crafts inequality. Versus U is a carry random variable who is associated with let equal to x1, x2, xw, xi are DRE random variables. W is a random variable. So E of W is summation of Wi, U of Ui. Okay, where Ui is assigned code word x1, x2 up to xwi. Then we have the graphs inequality, which says there exists a prefix free code whose code word lengths are the positive integers w1, w2 up to wk if and only if summation d minus wi is equal to 1. Then we have path length lemma, which says in a rooted tree with probabilities, the average depth of the leaves is equal to the sum of probabilities of the nodes including the root. Then from that you also have the leaf entropy H leaf is equal to minus summation Pi log Pi. We define it this way. I is such that Pi is not equal to 0. So for a rooted tree with t leaves whose probabilities are P1, P2, Pt, then H leaf is minus sigma Pi log Pi. Then we have node entropy or branching entropy of node I whose probability is Pi and has branching and branch probabilities Qij over Pi, j greater than equal to 1 less than equal to Li is Hi is equal to minus summation Qij over Pi log of Qij over Pi. So all j such that Qij is not equal to 0. From these two definitions, you have the leaf entropy theorem. H leaf is equal to summation Pi Hi for all nodes. So if there are n nodes, you sum from I is equal to 1 to n. Using all these results, we finally get E of W is greater than or equal to H of U by log D. Then you can do Shannon-Fano prefix tree board where the length Wi of code word for Wi is ceiling of minus log of E of Ui log to base d. And this gives you E of W less than H of U by log D plus 1. From this you can write E of W greater than equal to H of U by log D was already there. You can also write H of U by log D plus 1 because this Shannon-Fano coding achieves seeding of H of U by log D. So at worst you can do Shannon-Fano coding, or you might do a better coding if you have a better coding. Then the optimal coding scheme is Huffman coding, where you use the facts that the binary tree of an optimum binary prefix tree code has no unused leaves and two least likely code words in it differ only in their last digit. By using these, you have a algorithm, which is Huffman coding, which gives you the optimal prefix-free code for any carry random variable. You can extend this to DRE random variable, DRE coding, except that the number of unused leaves in the final stage is the remainder you get when you divide k minus d into d minus 2 by d minus 1. So you have to, if you call that as r, which is number of remaining leaves, then initially you should have d minus r leaves likely code words, which differ only in in their last digit. That's in the first stage. But afterwards, you can use the same algorithm that you use for the binary case. A similar algorithm. You can go search the exact algorithm, see the exact algorithm in the lecture videos for week 2. Next, this is all the results for single coding of a single random variable, for coding an information source use LBlock parser, we have U1, U2, etc. Which comes out as V1, V2, etc. Where V1 is U1 to UL, V2 is UL plus 1 to U2L, etc. Then you have your L block to variable length coding will give you EFW expected value of the code word length is between per source letter is between HFU by log D and HFU by log D plus 1 over L. So by taking larger and larger values of L, you can get your EFW by L as close to HFU by log D as you want. So for you take an infinite, taking it L to be infinite is not useful. That would mean that there's just one code right here. It doesn't really make sense. Practically, you can't really take it. But L as L goes larger and larger, 1 over L becomes smaller and smaller. So EFW is restricted to a smaller neighborhood of HFU by log D. So it gets closer and closer to HFU by log D. The lower bound is already HFU by log D. Upper bound is HFU by log D plus epsilon, some value epsilon. The epsilon becomes smaller as L becomes larger. That's what we saw in week 2. Then you have week 3, where we saw variable to block length coding. You had V is U1, U2, so variable length parser is associated with the block code x1, x2 up to xn, where the x's are really random variables and y is a random variable. E, E of y should be as large as possible. That's a goal of variable to block length coding. Then you have its leaf, the proper message set is the equivalent of a prefix-free code in this case, and the proper message set can be associated with the carry rooted tree. Leaves of carry rooted tree. And in this case, you'll have h leaf is equal to h of v. Since the u's are all independent, you can write h of v as the average over all is the average length times uncertainty in u. Let me write it. You can write this is the expected value of minus log of PV of v. This is the expected value of minus log of v u1 to u y of u1 to uy. This is the expected value of is there independent sigma log e of u I is equal to 1 to I times pu I of u, which is expected value of log pu of u into y. And y and u are independent. So y doesn't really depend on u, so you can write this e of log e of u times e of y. So this becomes h of u times e of y. And you also have the branching probability is h of branching entropy h of y is equal to h of u. Now h leaf is equal to summation pi hi is equal to h of u. Okay, this is the derivation from the tree. I'll write the result directly then. E of y times h of u. If you do prefix free coding of a proper message set, you get E of w by E of y greater than or equal to h of u by log d. And you have a tungstal coding for which you have tungstal message set where m is equal to k plus q into k minus 1. Extend starting from the root. The most likely leave q times. So this tungstal message set maximizes the average message length EFI. To find q, you have to if d power n greater than or equal to k, then q is m minus k by k minus 1. Or d power n minus k by k minus 1. This should be an integer, otherwise you can't really get a tungstal message set. From this you get e of y by n is less than log d by h of u, greater than log d by h of u minus log of 2 over t min by n h of u. Next, we have results on the asymptotic equipartition property, which is useful for block-to-block coding. We have the weak law of large numbers. Says mu hat of xn is 1 over n summation of x of k is equal to 1. If you take the sample mean, then mu hat of xn approaches the true mean mu of x in probability as n approaches infinity. From this, you can write Chebyshev inequality. In, you don't get Chebyshev from that. Chebyshev inequality is also needed for further results. So we'll write E of mod of x minus mu of x greater than equal to epsilon is less than sigma x square over epsilon square for all non-negative epsilon. And from this you can get P of mu hat of x n minus mu x less than or equal to epsilon, or you can write it greater than or equal to epsilon is less than or equal to sigma x square by n epsilon square. So that's combining weakly applied numbers with Chebyshev's inequality. From that you can write P of NAI by n minus P of A is greater than or equal to epsilon is less than P of A into 1 minus P of A by n epsilon square, where event A occurs n of A times in n trials. Then we define a typical sequence. There is a sequence such that the number of times the value AI occurs. The sequence of it's an n-length sequence of some random variable that can take k values. So if you do L trials, you have L trials, then AI occurs in any I of u of those trials. If any I of u by L is within epsilon of pu of AI, for all the source letters, then it's called a typical sequence. From this, we can prove the probability of a typical sequence is between 2 power minus 1 plus epsilon LH of u and 2 power minus 1 minus epsilon LH of u. And u is a typical sequence. It is U belongs to the typical set. You can also show that 1 minus P of F, where P of F is the probability that a sequence is not a typical sequence, is greater than 1 minus K over L epsilon square P min. So P of F, the probability that a sequence is not a typical sequence, is bounded by upper bounded by K over L epsilon square P min. So by choosing proper values of L and epsilon, you can make probability that it is not a typical set as small as possible, or the probability that your outcome is a typical set is in the typical set to be almost equal to one. Finally, the number of typical sequences M is bounded as M greater than or equal to 2 power 1 plus epsilon LH of U, sorry, M less than or equal to that, and greater than 1 minus K over L epsilon square P min 2 power 1 minus L epsilon LH of U. You can select K over L epsilon square P min is equal to epsilon by properly choosing L. In that case, you can just write this down as 1 minus epsilon times 2 power 1 minus epsilon LH of U. So we call these three results the AEP for large L and small epsilon. There are roughly 2 power LH of U epsilon typical sequences. Probability of a sequence being epsilon typical is nearly 1, and probability of each epsilon typical sequence is approximately 1 over 2 power LHF. That is, the epsilon typical sequences are almost uniformly distributed. That is, the typical set has uniform distribution. As a consequence of AEP, you can do block-to-block coding. consequence of AEP or block to block coding, uh, L block, L length block of carry DMS can be encoded with N block with N length DLE block code such that the number of code letters per source letter is less than or equal to h of u by log d plus epsilon 1 and p of f. The probability that you decode wrongly, erroneously, is less than epsilon 2. But we can also show that if your PFF is less than epsilon 2, if you want to make that, you can't have arbitrarily small uh, n over l. So as you decrease n over l, the probability of uh, error will also increase. So to keep the probability of error up, average probability of error up, you will have to increase n over l. So you cannot arbitrarily decrease the rate n over l. So we are out of time for today. I was only able to summarize three of the lecture videos, three of the weeks, 3 weeks worth of lecture videos, or three lecture videos. For the remaining 5 weeks, you have to make your own notes. I'll share these notes on the drive as usual. You can make use of them and extend them further to other content in all the other lectures also. All the best for your exams. Thank you.